Okay, welcome everyone. You have found yourself in the 3DEP for the Nation interest group meeting. Just by way of information, if this is your first time on a 3DEP for the Nation interest group meeting, 3DEP for the Nation is a cooperative agreement between the National State Geospatial Information Council, known as NSGIC, which is a membership organization between state geospatial information leaders uh, that exist to foster collaboration, information sharing, and innovation on geospatial technology between states. So the NSGIC 3DEP for the Nation program is a collaborative agreement with the USGS, the United States Geologic Survey, 3D elevation program, and I'm throwing a lot of acronyms out there for anyone who's new to the scene. Um, the 3D elevation program is run by the USGS. It's a way to minimize spending on nationwide elevation data. So they pool money from different federal agencies, states, and even private entities to collect LiDAR data and produce really high resolution elevation maps across the United States. It's pretty incredible. So the interest group meetings are a place to bring stakeholders together to learn about what the program is up to discuss different types of use cases, and to generally share information and learn more about elevation across the nation. So I'm going to go ahead and share my screen here. We've got a really exciting meeting lined up today. Let's see. We have with us, what we're going to do is we're going to go through um, a couple of updates in the USGS side of things. And then we have a presentation from Kurt Shalais as well. I'm sorry, Kurt, if I mispronounced that. I should have should have done that beforehand. And another meta engineer who are behind the um, Overture Maps building footprint and building heights. So they use 3DEP data to derive those building heights. Man, I am okay. This is not, my screen share is not cooperating. Sorry guys for the technical difficulties here. Let me see if I can get this going again.
It was there for a hot second, Jordan. It
Thank you,
was just
Chanel.
there.
It's like I've got too many windows open, of course. Shut everything down. Right. All right, there we go. Cool. Thank you for your patience here. All right, great. So for those who joined a little after my explanation, you are in the NSGIC 3DEP for the Nation interest group meeting. This is an open forum designed to help folks get updates on the 3D elevation program run by the USGS and to collaborate with states on their participation in that program as critical partners. So today we are going to get a quick USGS update. As a lot of you guys know, there's a lot of things going on in the federal government, so that will be pretty short, but hopefully I can build some excitement there. I'll run through what we're up to with 3DEP for the Nation. I'll send a couple of reminders, and then we're going to have an awesome presentation about how the 3DEP data was used to derive Overture's building heights. And Kurt will be presenting there. So as far as USGS goes, FY24 wrapped up with coverage for 98.3% of the nation covered in high resolution elevation data. So most of this data is LiDAR derived point clouds producing a 1 meter digital elevation model. So this map over here, the dark green, are projects at the end of FY24 that are completed or in progress and soon to be published to the national map. So pretty incredible coverage. The program has been going on for about 6 years now. So excited to see that progress and to reach 100% coverage for the nation in high resolution elevation data. As the federal administration and Congress are transitioning, we are waiting on more information and guidance on FY25, but hopefully those things will be cleared up soon, and we can really showcase the value of the program and reach those the technological prowess that folks are building excitement about through this really innovative data. And unfortunately, Brian has some personal and administrative things that is extracting him from today's meeting. But hopefully at the next interest group meeting, we'll have an opportunity to hear from Brian and ask him more questions and get more details here. So I'm going to move on to the NSGIC 3DEP for the Nation project update. We are publishing the 3D National Terrain Model Planning Guide. So this is a guide to that was done in conjunction with the 3D hydrography program to help states understand and implement best practices as they collect and produce this data within their states. Our FY25 focus areas, sustainable funding is always at the top of the list. This program is really expensive, but by pooling dollars and putting them to use in a partnership model, we really stretch those dollars, whether they're taxpayer dollars or private partnerships, to help fund this data and make it available to folks like Meta and Overture Maps Foundation, and pretty much any large geospatial platform is integrating 3DEP data into their topography layers. So a lot of value there. So securing sustainable funding is at the top of that list to make sure that this data continues to be produced. And then we're helping to facilitate derivative products and data distribution, so that those are things like building heights, elevation models, wind paths, all sorts of things being produced from these foundational LiDAR point clouds. So helping states understand, what is California doing well and what could another state learn from, or what is Illinois doing really well that another state can learn from. And then, of course, 3D hydrography program coordination. So 3D HP, water shapes the topography and topography shapes water. Those are two really important aspects of our land and understanding our geospatial systems. So how can states orient their 3D elevation programs to make sure that they're best positioned to produce those hydrography components? And then states do a ton of work acquiring and producing elevation data all on their own. And so we're working on helping states and USGS collaborate more on contributed data, so that it's not just federal dollars, but we can also leverage those state efforts and incorporate that data into the national map and use it for all sorts of awesome stuff. Does anyone have any questions on what NSGIC 3DEP for the Nation is up to in FY25? Cool. All right. Got a couple of reminders, and then we're going to get to the real meat of today's meeting, which we're super excited about. I'm sure a lot of you guys are joining to learn about Overture's building heights. But coming up in the first week of February, we have a 3DEP for the Nation state team meeting. So excited to talk to states and really hear how you guys are doing and approaching FY25. I know a lot of people have things on the top of their mind and how we're going to approach FY25. And then coming up at the end of February is the NSGIC mid-year meeting in Colorado Springs. If you are a business partner or a geospatial business that is not involved in NSGIC, but you work with states or you sell to states, or you're just building cool stuff and you want to see what states are doing, I highly recommend attending the NSGIC conferences. This is a great time to meet folks within the industry and understand what's going on from a state perspective. We will have 3DEP programming there. The 3D NTM breakout breakfast is on that first day. We'll hear updates from states and collaborate in person around what we're doing. And then we'll be discussing that letter that I mentioned in the previous slide on how to most effectively contribute data to USGS 3DEP program, and advice and recommendations we have for USGS around the acceptance and validation of that contributed data. So that's what we got coming up. Happy to, hopefully we can see you guys at some of these upcoming events, but I don't want to spend too much more time taking up space in the meeting. We're very excited to welcome Kurt Chalais and Benjamin Clark, both from Meta. These are folks who are behind the deriving building heights that is now available within Overture Map Foundation's building themes. So Kurt and Benjamin, welcome. Excited to hear from you guys.
Yeah, Thanks, Jordan, and hello, everybody. I'm Kurt Shalhaza, and Jordan, you got very close. Nobody ever, closer than most people. So I give you A plus on the last name. It's a tough one. But yeah, nice to meet everybody, and some faces I recognize because this was a collaboration with the USGS when we did this. So I understand we have a range of kind of diverse audience here, from technical people to kind of more government business case type people. So as we go through this presentation, I'm going to be putting on lots of different hats and trying to cover why do we do this and how do we do this. But we'll have about 15 minutes for questions at the end. But I'm going to pause about halfway through and take questions because I want to make sure that we don't get deep into the presentation without people understanding why we did it in the first place. So yeah, well, we can keep this casual is all I'm saying. And feel free to use the raise your hand button. So let me go ahead and share. Everybody see this okay? Maybe screen sharing. Okay, I'll assume you can. Okay, yeah, thank you for the thumbs up. Let's see, how do you? Oh geez, view full screen. No. I feel like I'm having a how does technology work moment. Where's oh, there it is. Okay. Okay. Now we're gonna talk about advanced technical stuff after I couldn't find the share screen button. So yeah. So this was work done. Let me set some context here. This work was done as part of Overture Maps launch. So it's one of the very first use cases Overture did. And it's a really great use case for Overture. And I'll talk about what Overture is and how this relates to it, but you'll kind of see as we go along, like this is a great use case for Overture that'd be really hard to do with other kind of open map systems out there. And the reason is because it's so much diverse data sets coming into one unified layer, and that's pretty challenging to do at scale sometimes. So just to give some background information, also Benjamin Clark is here and he'll introduce himself in a second. But yeah, we'll cover the background information, our plans for scaling, what was the technical details, how do we actually make sure that this is accurate data? We always want the map to be as accurate as possible, but what was our QA approach? And then kind of the challenges. I understand like a lot of the people here are also producing the data. So I also thought I would give some challenges as far as like, think of us as like a typical user of the USGS data. Like we're just general software engineers with some geospatial experience, and we just grabbed the data and ran with it. So we can kind of give some feedback on what was challenging for us and what was, maybe you guys can teach us some stuff about the data as well. So let's talk about the motivation. So, and then I'll talk about what Overture is after this. But our motivation was we were really interested in getting a richer display map. And I'll talk about, there's a couple different use cases that these building heights give us. So that first off, in the top right image that you see, this is OpenStreetMap buildings with the OpenStreetMap height. So there is height data in OSM today, which if you don't know what OpenStreetMap is, it's like a Wikipedia of maps, one of the largest used open map source projects in the world. And all these polygons are probably hand-drawn by the community. In fact, they most likely are. And what the community is also starting to do is add height data. And some of this can be publicly sourced, like through Wikipedia or just kind of, there's not a lot of sources out there that are authoritative. And I think that's the problem for scaling. It's like when you're a company, like one of the big companies like the Googles or Apples of the world, you can do kind of photogrammetry at scale and kind of get these heights. But when you're kind of like the, typical mapper or, like when I map an OpenStreetMap myself, you only have the data you got. So we want to make this data more accessible. And we knew that like there's a lot of height data missing in OSM today. So we did some basic kind of queries where at the time, which was early 2023, only 20% of US buildings had a height value at all, which makes sense because there's only so much authoritative height data out there. In fact, they're less than 10% globally. So the US actually had a little bit coverage compared to the rest of the world. And what we saw was kind of this opportunity of LiDAR data is publicly and freely available from the USGS, but doing this kind of computation at scale is a little bit difficult because it does require a lot of compute power. And so as we were looking at this project, Overture was also starting to kind of form and get together. And we had a couple different things going on that kind of brought this use case together. So again, like this use case was focused on a richer display map. And you might see this as you drive around with other kind of if you have like the typical navigation apps, you'll see that more and more they're showing these kind of 2.5D representations. And one of the benefits of that is it kind of helps you orient you to the world. Like for this example, if you're looking at a flat 2D map and you're on this corner, it's a little bit easier to orient yourself because the green side is over here. But if you're in the middle of the city and you're surrounded by tall buildings, or on one side and short buildings on another side, it can also help you orient a little bit as you move around. So that's one use case. There's a couple other use cases out there, including augmented reality use cases. So this one's a little bit more atypical, but you might also think about, these are also references for augmented reality artists. Like somebody can use this to know, hey, if I want to position augmented reality art on top of a building, I need to know how tall the building is. Or if I want to throw an augmented reality ball and bounce it off the side of a building, I need to know how tall the wall is. So there's also use cases like that. And you see other companies like listening about the Niantics of the world or the Pokemon Go's of the world who do this kind of stuff. So we want to make this publicly open and free to everybody, but also, again, realizing that this does require a lot of compute power. So it's not something that the typical kind of OSM mapper would be able to do, but it's something that Meta can help out with and Overture can help out with, because we have the world's biggest computer, right? We have a lot of compute, no shortage of machines to run this processing on. So as we go through this use case, I'll talk about how we made our design decisions, but ultimately our guiding principle was keep it simple and keep it explainable. So for example, we could get really hardcore into all the different edge cases. There's over 2 billion buildings in the world. But overall, you'll see, I'll go into more details as we get to the technical part. We wanted to keep it simple, but our motivation for this use case was a richer display map and giving this back to the community. So again, like if a mapper did want to add this map, they would be able to get this data. So with that, I mentioned the word Overture a lot. What is Overture? So I'll also invite Ben to kind of give a take here, but I have a couple slides just to introduce Overture. And at the end, we'll talk about how can you get your hands on this data as well. Because that was kind of the point, is give it back in the open. But Overture Maps was founded really to make it easier to get reliable, easy to use open data at scale, and something that we would call more production ready and QA'd. So OpenStreetMap is amazing, but at the same time, you're at the mercy of whatever data happens to be out there. So we run a whole lot of automated detections on geometry errors, vandalism, things that you may not want in a corporate style base map. So I've also heard Overture Map called as an OpenStreetMap for developers. So that's another way to look at it. But I think the big theme here is that it's open. It's the same license as OSM, and it's interoperable. So it really makes it easy. So one thing with OpenStreetMap is it's heavily discouraged to do automated editing or editing with pipelines, which makes a lot of sense, right? Part of the magic of OSM is that it's from community editors with local knowledge. So if all these corporations came in and started doing automated edits to OSM, that would kind of hurt the trustworthiness of the data or the source of the data. So Overture is a good landing ground for these kind of changes. Like as one of the first steps for this LiDAR work, we needed to merge Microsoft machine learning buildings, over 2 billion predictions for machine learning buildings from Microsoft, billions of predictions from Google, Open Google Buildings Dataset, OpenStreetMap, Esri, our partners, we partnered with Esri on this, which I'll talk about in a second, which they brought really awesome data sets from local GIS departments that was aggregated through the Esri community maps layer. So all of these coming together in these kind of automated fashion would be really tough to do in OSM by itself. But Overture kind of gives this good landing pad for, hey, we did all this processing. We want a good place to give it back, and some place that we can say, hey, it's been QA'd, it's been verified, we have confidence that this is good, accurate data. So that's how I view Overture Maps. But Ben, I wanted to invite you to introduce yourself and also give your take of what is Overture Maps.
Hi, everyone. Yeah, by way of quick intro, I'm Ben Clark. So I, like Kurt, I'm a Meta software engineer. I also have another hat to wear here, as I'm also the chair of the developer advocacy task force within Overture. So it's that task force's job to sort of help people who want to adopt Overture data and to help them flag any issues that they have with uptake of Overture data. So if you have questions about that, we can certainly talk to those. I think Kurt, your synopsis is great. Really to hammer home the idea behind Overture Maps data is that it is schematized data. So if you're looking at OpenStreetMap data and say you're a software developer that wants to like write a transportation routing algorithm, well, you're going to have to worry about all the different tagging idiosyncrasies that are inherent in, say, routing somebody through London versus routing somebody through Lisbon, depending on the local mapper, customs, and conventions. You're going to have to write slightly different software to route people around every city on the planet. And in some cases, individual neighborhoods of the same city might be mapped or tagged slightly differently. So Overture is partially, I think you can think of it as an answer to that problem, where like having a single unified cohesive schema to all of this data, and it's the Overture Maps Foundation's sort of pledge to the community that we're going to try to consolidate all these different sources of open data and put them into one cohesive, coherent release.
Awesome. Yeah, and great segue, because the community is growing, but this is like a snapshot of companies in the moment, but a lot of people are joining every day. And if you're interested in joining, feel free to reach out to Ben, or just looking to learn more. And just to kind of summarize before we go more into the technical details of how the LiDAR use case fit in here, but this is very relevant, is we wanted a world where we can take these proprietary assets that companies typically keep behind closed doors and open it up, because we've kind of seen over time and time again that open source is the path to the best types of data or the best type of software. So we want to kind of have that spirit and give this back. So not only did we kind of process this data, but we wanted to have that vehicle of Overture to give it back to everybody. So I'll kind of glaze over this slide, since a lot of people here know what 3DEP is, I'm assuming. But the main thing I want to cover here is, and you can tell that this is a couple years old compared to the figure Jordan just showed earlier. So this is the map of everywhere we had QL1 and QL2. So this was like the highest quality LiDAR data for us. And so, and with 0, 1, and 2. So this was our focus area, where we're like, okay, our first step is what kind of data is out there, right? We have all this kind of LiDAR data, but where do we start? And we start looking at the highest quality to start with. And so what we started with is, okay, we have all this LiDAR data. Where do we start and how do we roll it out? So I'll give a kind of an overview of our roadmap, and then I'll go into the technical details of how we processed it. But basically, what we first said is what cities in OSM are missing the most height data. So what's kind of the juiciest areas to get that height data back? And then where do we have the high quality LiDAR data? So kind of the intersection of what's missing in OSM and where do we have QL 0 through 2 data? And the red is kind of that final output of, and so we're like, okay, and these were also major metropolitan areas that were focus areas for areas we want to improve on our roadmap. So this was kind of our natural starting point. And so we kind of figured if we can nail these cities, scaling to the rest of the US will be pretty easy after that. But we also realized, like, somewhere in the middle of Kansas, we don't want to process areas that don't really have a lot of buildings either. We want to say, like, what's that balance between spending money on compute and then having an impact with the, best number of building heights. So this was kind of our rough approach. But like, just to give you an example, when we initially released the data, it was around 6 million LiDAR heights, and currently it's about 11 million. And what we can do is, and actually this is on our to-do list, is as these new LiDAR work units get processed and released, we plan on kind of updating this and kind of, again, doing that search of where do we need it. So let me talk first about, like, okay, so we kind of identified some focus areas. What's next, right? Now it's time to start coding. So I'm going to start kind of diving into the technical side. But before I do that, I'll take a couple questions. If there's any just motivation questions, why do we do this? What's the impact? Any type of quick questions that might help the group at all? Let's see.
No questions in chat yet. I've been monitoring,
Okay.
just in
Yeah,
case.
I'll just keep going then. But yeah, feel free to let me know if I missed something. I can't see the screen, unfortunately. Let's see. Okay, so I think the first step was create a spatial index. That tends to be the first step with a lot of kind of geospatial projects like this. So a lot of our stuff in Meta is done through Python and SQL and big batch pipelines. Like, that's kind of our bread and butter, is like big batch pipelines and working with stuff in Hive. And so there's a really great geospatial index that's put up there by the USGS that where essentially the shapefile version of this, where I can click on a work unit, see its metadata. So what we did was we put that into a fixed schema and put it into a Hive table. And so that way we could query and plug that automatically into our pipelines. And we kind of based everything we did off the USGS work unit. So what we do is we say, hey, this Austin, Texas work unit is a very juicy work unit, high quality, low amount of heights in OSM. So we're going to adjust it. So we built a downloader that we would punch in the work unit name. It would auto download that from the USGS S3 bucket into we have like an internal version of S3 that's basically S3. And so we would copy that in, and then we would, but then we were like, okay, that gives you the top of the building, right? So with the LiDAR, you can get the top of the building, but the question is, okay, what is the definition of a building height anyway? That's good to cover, right? Like, what's our goal? In OSM, they define a building height as the highest point of the building from the lowest point of the building. Or essentially the ground level, right? But also exclude stuff like antennas and satellite, like stuff that is kind of, let's say, not part of the building, but might be attached to the building. So that's a little bit difficult too, because you think about it, those antennas and those satellites are probably going to get caught by the LiDAR, right? It's going to be a point cloud there. So that was just one consideration. So we built a downloader to get the top of the building, but we also realized we need to get all of the DEM data. The USGS not only puts the raw point clouds out there, but it also puts the calculated terrain. But we also realized to do this at scale, we're going to have to build a service. So we had to do a quick pause. We built an entire terrain service where, again, we downloaded, for this, we actually downloaded the entire US map of the terrain. It's a little bit smaller data size. Obviously, it's like, then the raw LiDAR data, the DEM tiles are a lot more compact. So what we would do is we basically built a service where we give a lat long, and we could do, asynchronously. So we do 100 calls to the service and say, hey, for every vertex or every corner of this building, give me the terrain. So that's kind of how we found the lower bound of the building, was through the service we built. And then what we realized is, sometimes if the building's near a coast, you might have LiDAR point cloud data, but you may not have terrain data at all. So we also had a fallback service of the MapZen tiles. If you're familiar with MapZen, they put out some public terrain tiles. They're much lower resolution, not nearly as good as the USGS, but that was kind of like a good fallback option, because sometimes we didn't have the terrain near the coast if there was like a building on the beach or something. So yeah, that was just one quick side note. But to make this happen, this is how we got the bottom of the building, was kind of having this USGS DEM terrain service that we could ping all the vertexes of the building, and then I'll tell you in a little bit how we used LiDAR to get the top. But as you can see, it's like, it was really important to visualize this data, because basically, as I mentioned, we went for simplicity, but there are so many different types of buildings out there. Think about like a dome roof or a cone, or I'm here in Seattle. In Seattle, we got Pike's Place Market, where the sign is bigger than the building. So it was really kind of interesting to look at these and say, okay, what is the raw data we're looking at? And so next I'll talk about what we did. So as you see, this was the raw point cloud. And what we said is, okay, out of simplicity, let's take a vertical view of it, and let's make a cookie cutter with all the buildings, right? And I mentioned, again, another side project was, besides just building the terrain service, we also needed to get all the buildings into a unified layer. And so you can see we had all these different building footprints. Much of them are global in scale. And I'm just going off the top of my head, but let's say like OpenStreetMap had roughly 1 billion buildings. The Microsoft and Google buildings releases had another 1 billion that were not in OSM. So combined, there was like 2 billion. And then there was hundreds of thousands of Esri community buildings. And these are some news sources that weren't there at the time, but I thought I would mention them, which is kind of a European data set. So basically, one part was another huge pipeline to conflate all these building footprints. Thankfully, conflating building footprints into a single layer is pretty straightforward as terms of like an algorithm, right? You can do building overlap and make sure that that check passes. But the real difficulty is doing that at the global scale. So again, like this was part of the, where we had to go through these 2 steps of, one, getting all the building footprints together, and then doing all the LiDAR work. That's one part that Overture can help with if you do something in the future, is like, instead of doing all this conflation to start your project off, you can just go download the Overture buildings and basically save all the work that we had to do going into this. So just want to point that out, as this is like a great time-saving opportunity. I meet a lot of people at GIS conferences who tell me how they're kind of still doing this as an initial step, or the Microsoft buildings data set's very well known. Just want to point out, like, this is a good time saver in the future. So okay, again, just to rewind, so we have all the raw data now. And then so now what we've done is we took in this top view, and this is more of a visualization of saying, hey, if we remove all the LiDAR that does not intersect a building polygon, this is what you're kind of wound up left with. And so from here, we would make a DSM, or digital surface model. So basically, we kind of take all the point cloud data. It's really tough to work with all those points, and we kind of merge it into a single mesh. And then I like to think of it as, this is kind of a funny analogy, but the LiDAR is the flour, the DSM is the cookie dough, and then the buildings are the cookie cutters. So that's kind of the progress how we went through of like, okay, we didn't want to work with the raw point cloud data itself, so we got the DSM and then cookie cut it. And then once we have that, it's time to estimate the height. And I'll talk about some challenges, but at the most basic level, we would look at all of the heights within the DSM and take the 98th percentile. But it's not always that simple, right? So in an ideal world, the USGS work unit we're working with has point classification, which was completely awesome. Like we did a couple analysis where I'm kind of going off memory here, but whenever, and for those who don't know, you have the LiDAR point cloud data, and it can come with up to 6 classifications. Is this point a vegetation? Is it concrete? Is it the terrain, or is it a building? And building happens to be one of the point classifications. So when we had that data, it wasn't always there, but when we had it, it was extremely accurate. Like getting the building height using the 98th percentile was very accurate. When we didn't have classification, or all we have is just the points, we did see a lot more noise or less accurate data, but still within good margin. I'll talk about the statistics of the accuracy in a bit, but I just want to point that out, that like building classifications are awesome, or point classifications are awesome in general. Now, another issue or consideration is the LiDAR data comes in tiles. So you have a work unit, but you might have, if you're taking the raw data from the S3 bucket, you might have thousands of these tiles. So obviously a lot of these buildings are going to cross the tiles. So how do we approach that? So we did a 2-stage process where we process each tile individually, and then we output the results to a staging table. And so let's say this building here in the bottom right crosses 3 tiles, for example. So what we would do is we would get, before we take the 98th percentile, we would create a histogram saying, hey, this building was in this tile, and here's a histogram of all the height values in that tile. And we wouldn't take the 90th percentile yet. So once we process each tile, we would do a final step to aggregate that histogram and then take the 90th percentile. So it's basically, it's like taking a bookkeeping of all the building heights found in a tile for a given building ID. And then that way giving us all the statistics or numbers we need to take that 98th percentile later. And so, yeah, that was just an important consideration of like, well, how do you process the tile by tile aspect? And I might think of a couple other considerations as we go through, but I just wanted to point these ones out of like, and again, simple and explainable. We did look at routes of, hey, if it's a dome shaped roof, maybe we do this. If it's a flat shaped roof, maybe we do this. And we even did some work of like, hey, taking the LiDAR point clouds and using machine learning to classify it into a roof type, because obviously like you might have a roof type in OSM, but it's not likely to be there. So you're gonna have to like classify and detect yourself. And we kind of went down this route of getting really advanced with it, and then kind of coming to the realization that it's probably unnecessary or a little bit extra effort, but it could be done. But in terms of scaling and simplicity, we want to start with this as like a crawl, walk, run approach. And we said, if there's demand in the future for this kind of data, we could, in theory, go back and give all the roof shapes back to OSM potentially. But again, once we go with that ML route, you're losing a lot of your accuracy and your explainability. Why was it a dome-shaped roof? We don't know. The ML model said so. You kind of go down that route. So we wanted to avoid that. So that was, again, at the most basic level, we used the histogram approach and the tile approach and the 90th percentile to get the top of the building. We had the DEM, where we would take every vertex of the polygon and get a DEM ping to get the lowest point. So then we're matching the OSM definition of the highest point to the lowest point. And what we found is that the 98th percentile avoids those scenarios of antennas and satellite dishes. It just seemed to be a good number. We kind of did an approach where we tried every number from 90 to 100 and see what gave the best overall generalized approach. And how do we measure that? So here's a little bit of how we measured our obviously once we got a height, we have a height, but you don't know if it's ground truth. So we did find a pretty clever way to get some ground truth and compare our accuracy. So what we did was we took a work unit and we statistically sampled it for buildings to QA against. And so what we said is like, here's an example for Dallas. And we said like, well, we want 30% buildings that are in an urban area of high building cluster. And we want 30% that's more rural or like a residential area. So we didn't want to just QA ourselves on only urban downtown. We want to say, well, how's the distribution? How are we in kind of the mid area, high area, low area for each work unit? And so that was kind of our goal. And what we did was, well, where do you get the ground truth, right? You have the LiDAR height and you have a sample, but what's the ground truth? So we were fortunate to have some oblique aerial imagery from a vendor. And basically what we did is we had an internal tool where you could look at 5 images of a building and click on the same point. And if you know the camera's angle and all the metadata of the camera, you can basically create your own control point. So for example, if I click on this little corner here in 5 different oblique images, I can create basically a super accurate pinpoint. And then if I click 5 more times at the base of the building, I can get a height. So you can get a Z height from here. So basically what it would mean is, I forgot how many samples we did. So we did over 10,000 buildings. So for 10,000 buildings, we had somebody click 5 times on the top, 5 times on the bottom, and that gave us a super accurate height. And it also accounted for all the edge cases. For example, for this, I don't know if you see my cursor, but it's like we would give them instructions on where to click. They went that way, it matched the OSM definition. It was a pitched roof, click on the top of the pitched roof. Flat roof, don't click on an AC unit, click on the corner of a building. So that was kind of our approach for getting a ground truth. It's not as scalable because it requires you to have oblique imagery, but it was kind of good for the statistical case of like, hey, let's sample these 10,000 buildings. This is not the biggest number. We can work with our QA teams to do it. But this is how we got confidence in our results. And so there's also a question of what is accurate enough. So we quickly realized it's not realistic to expect like, with the broad definition of OSM, you can't expect like a 0.01% error because all buildings are so different and the definition is very loose from lowest point to the top point, right? So what we realized is that a vast majority of buildings are within 1 meter error, and we tend to over predict a little bit. And there could be some theories for that. Like there's always something on top of the building. That's kind of the leading theory, right? There's always something up there generally. So that's one reason that we predict over the course of 10,000 buildings, we over predict a little bit. But what we saw that was kind of, encouraging was that like all the work units were pretty much the same margin of error. So we didn't see like, oh, this work unit is way worse than the other work unit. Like it was pretty consistent. But like I mentioned, if the work unit had classification on all the points, we saw a lot tighter grouping of this accuracy bar. So I don't know if this is a good example or not. I can't recall. I think, yeah. So Santa Clara here did have classified building points where Arizona did not. So I think what you can kind of see is like Arizona, the blue is a little bit more right-tailed, right-leaning. So this is just kind of highlight that point. Now, you might be asking, what are these outliers over here on the right? And this was probably the biggest limitation of this approach, is that for residential areas, you're fighting against trees that are taller than houses. So that was a big problem where it's like, especially depending on where you're at, like there's always, it could be just something tall next to the house, and that would kind of throw us off. Or I'm trying to think, this was a bigger problem in areas like Washington, where, you might have a 50-foot tree, and less of a problem in places like Arizona. But yeah, that was one limitation. When we had point classifications for vegetation, that did help a lot. But just to kind of point out where it's like, you can't get them all right. And I don't think you can have the expectation that you'll get them all right unless you go really fancy, complex, over-engineered algorithm. But I think for the vast majority of buildings, it's pretty darn good. So I'll quickly talk about some technical challenges, and then Ben will kind of talk about how you can get your hands on this data. Like how would you kind of get started with Overture data? So again, I mentioned at the start, this is my take as kind of somebody who just dived into the data and started working with it. So I think one tough thing is noisy sources of ground height. So again, I mentioned that we use the DEM to get how do you get the bottom height of the building? So we also thought about approaches about like, oh, maybe you don't need the DEM. Maybe you just use the LiDAR building, right? Like maybe you just take a square around the LiDAR building, take the lowest and highest points, But what we realized is like the LiDAR is really accurate. So if there's a street light or bushes in front of the building, that's going to be kind of a, that approach isn't going to work. So yeah, it's interesting because like the DEM is kind of an average of the ground height that's kind of engineered. But yeah, that was just one challenge. But I think the DEM is a great mitigation towards that. Or sorry, yeah, and the DEM can have noise too. So we did realize like when we were doing those manually annotated ground or top and bottom of the buildings, there was noise in the DEM that wouldn't align with the ground truth control point. And so yeah, we also thought like, oh, well, you could maybe do something fancier where you estimate it all from the point cloud. Anyway, this was kind of an open topic. We went back and forth on it a lot, but ultimately, for the sake of simplicity, we went with the DEM. I think that was the best approach. So one thing we did realize is there are point clouds with classification that aren't as high as a quality as other work units. So for instance, when we started processing Florida for Miami, or I think it was Orlando, it's FL Peninsular was the work unit, we realized we actually got worse results with the classifications turned on. So, and we looked at the data and what we realized was like, there were sections of that work unit where the classifications were perfect, and there were sections where the point classifications weren't as good. So when we said, hey, consider all points and don't consider building classification, we actually got more accurate results for that work unit. So yeah, just something to think about too is like, this is major data at scale, so you can't always assume the building classifications are perfect, but when they're there, they were generally very helpful. This one was probably, for the technical people in the crowd, you were probably thinking about this, but yeah, there was a big OSM is mapped on like typically Bing imagery, and the LiDAR is super accurate. So we were in a situation where sometimes the LiDAR was more accurate than the OSM footprint a lot of the times. So there's always going to be noise from that, where the building footprint we're using might be cropping out the tallest part of the building, for example, or it might be 1 foot of a shift off. And so ultimately what we realized was, you can't always control for that, and we can't go move every building in OSM. But what we found was that it was good enough. Like, yeah, you're gonna have misalignment, but almost like 99% of the time, we were still capturing the tallest part of the roof in the footprint. So it wasn't that big of a deal. But in theory, you could do more sophisticated algorithms to try and align the two. But we opted that would kind of ruin our goal of simplicity. Another issue was buildings change every week in OSM. So we actually used to run this every week, just in case the OSM polygon would change that we were using as our cookie cutter. And what would happen is we would take the OSM ID and the version number. And if the OSM ID or version number changed, we would reprocess that building. But actually, one thing that Overture does is Overture gives every building a stable ID now. So we actually didn't have this at the time, but we do now, where now, even if the footprint changes, or it gets added in OSM or changed a bit, but you have the same stable ID. GERS stands for Global Entity Reference System. So that's a big selling point of Overture too, was like, that was almost a pain point for us at the beginning, is like, we were trying to deep dive on a building, but the building ID would change underneath us. And so kind of having this GERS is a good mitigation for that. And one more technical challenge, where there were cities that we couldn't really process because we did the assumption of one work unit, and it can't have any overlap. So we didn't handle the scenario of work units overlapping. So for example, like this is San Francisco, and there was like 6 or 7 work units that overlap. But there's other areas like Austin, this might all be one giant work unit. And as a developer or like an end user, it was always a lot easier for us to work with the single work unit, and that's how we set up our pipelines. So one limitation of our approach was, we wanted everything to be the same quality level. Like we didn't want to mix a quality level 1 with a quality level 3. So that was our approach here. But unfortunately, like we wound up not processing San Francisco at all. But we could technically do this little sliver here. But we actually found that already had pretty good height coverage in OSM. So again, it didn't kind of meet our criteria of something juicy to kind of tackle that was missing broadly. But this is something we want to revisit. And as new work units come out or new captures come out, we'll probably start processing more cities as those come available. And I want to hand over to Ben to talk. Ben's going to kind of wrap it up and talk about how can you get your hand on this data for those of you who aren't familiar with Overture. And then we'll take open Q&A after that. So Ben, over to you.
Cool. Thanks, Kurt. Yeah, we can pause if there are any other I do see a few questions here, actually, that I must have missed. Let's see. Okay, how many cities were you able to do, Kurt?
Yeah, good question. So I'll go back here. So I think it was 11 or 12. So basically all the cities in red are what we processed today. 1, 2, 3, 4, 5, 12 or 15, but yet I think there's room to grow. There's obviously a lot of room to grow. And so one thing I was going to throw out there is if anybody on the call wants us to run your city or you're working it, just let us know and we can prioritize that. But for us, we're kind of like slowly rolling this out and slowly taking our time with it. One of the things is all these cities in red, we've actually done the control point QA on. So we haven't done a lot of cities where we just process it and throw it out there without the QA or statistics yet, but we're kind of open to that if anybody has a request. So that's the short answer to the question.
Cool. Another question here that I'll take, which is with GERS, and that is our Geo Entity Reference System. It's perhaps not the most wieldy acronym on the planet, but it is unique. So if you Google it, there are no other GERSs that you will find. I think that is still true. So with GERS, are the building polygons now versioned to track changes through time? So the short answer to that is no. What the question is getting at is what I would call traceability, the ability to pick an entity in the Overture data lake and then say, okay, how has this building changed from release to release? Maybe we used a different source for the building footprint in a previous release, and now we're using this other one. We are starting to be able to answer this question. We are releasing what is known as the GERS changelog, but that changelog only looks back one release iteration. So we can tell you in a little bit of detail how an entity has changed from the previous month. But what we are hoping to do is expand our tooling for GERS this year to be able to answer that question. In fact, this is one of the things that's on my plate to sort of create this year, is to allow you to link into our Explore site with a GERS ID and see what an entity looked like in different versions of our data drop. Hope that answered your question. Cool.
Yeah. And Ben, one thing I forgot to mention before I hand over to you is in this bottom right image here, I wanted to point out that like we have a lot of different sources of buildings I mentioned, and you can see that like we add LiDAR heights where possible to any of the building sources, and LiDAR is the top priority. But we also have another source of height data, which is the Microsoft ML team came up with an ML algorithm to predict building height based on oblique imagery. But the thing is, they found that it's not as accurate in urban centers. So when we have LiDAR, which is an actual sensor, we take that height and put in Overture, and then the Microsoft ML height is a backup, but kind of has that more global coverage or that house in the woods type of thing. We can predict from that, and it deals a little bit better with trees. But as we start processing more of these LiDAR data, the LiDAR takes priority. But I just wanted to throw that out as an example of how we're merging all this data together from all these different sources. And then it's sourced like, hey, this height is from LiDAR, or this height is from an ML prediction, use at your own risk. So just want to hand that over as an example, or last talking point. But yeah, over to you, Ben, to kind of talk about this too.
Cool. Yeah, you can advance the slide if you could, Kurt. Cool. So as I said before, I'm the chairman of the developer advocacy. One of my jobs is to try and make sure that people can adopt and use the data without problems, and to work with folks that are trying to adopt the data. So for starters, we are interested in your data, and we will work to try and incorporate any open data that you have to share with us. We break our work across several different themes. So we have a transportation theme, a base map theme, we have places and addresses, and all of these different themes take data from kind of a wide variety of different sources. OpenStreetMap is, of course, a huge one that comprises most of our building layer and the near totality of our transportation layer, but addresses and places are actually sourced from different places. And this kind of gives us this very unique problem. And Kurt just touched on it a bit, where even just one piece of metadata about a building might potentially have different sources where we're grabbing it from. So just the building height could be coming from OpenStreetMap annotations. It could be coming from LiDAR data. It could be coming from different sources of LiDAR data. And so this gives us a bit of a problem when we create the Overture data sets to properly source or to display the source of a particular feature, because a single building could be comprised of many, many different sources of data, which we've all sort of cobbled together in the final product. One of the other sort of calls to action is if you do adopt Overture data, we are very curious to hear if the reference system, if GERS actually helps you do your month-to-month aggregation and conflation. So as I'm sure most, if not everybody here knows that, just doing a one-time join of two geospatial data sets takes some time, maybe not the worst thing. The problem is when you have to do this stuff over and over again, month to month, across an ever-shifting data landscape. One of the sort of North Stars for GERS is to be able to provide stability across different changes to a given entity. So if a building's metadata changes, we're not going to change the ID on you for no reason. So if the building number, I'm sorry, if the phone number of a particular place or if a building footprint changes slightly as we maybe source a better building footprint from a different data source, that the actual ID of the building will not change, making it easier for you all to do your spatial joins month to month. Because if your ID changes at the drop of a hat, the second any bit of your metadata changes, well, it's not really very useful from a stable perspective. So we have tons of resources to help you get started up on the docs site, so docs.overturemaps.org. We have our data and schema repositories where you can read up about the individual schema formats for each theme. There's like detailed schema JSON documentation to help you get familiar. You go to the next slide, please, Kurt. And I was also one of the driving forces behind creating this explore site for overturemaps.org. So this is actually all of our GeoParquet data converted into cloud native PM tile format. So it's pretty fast to load. You can inspect pretty much any place on the planet and sort of get a first look at the data schema here in this little inspector panel that you can see over on the left. This is live, something that Overture Maps maintains itself. And as I said, it's built right on top of the GeoParquet data that we release every month. So within a day or two of releasing the GeoParquet data, we make an update to this site. So it's pretty much always very, very up to date.
Ben, I thought this might be a good opportunity too. It's like, if I remember, you can get this in Snowflake and AWS really easily too. Is that right? Or
yes, if you go to docs.overturemaps.org, we have a couple of partners such as like Fuse, Snowflake. These are sort of like places where you can sort of use like big compute resources to start experimenting with Overture data. You can also do it the more old school way and load all of the GeoParquet to your local system and use QGIS or DuckDB to start like issuing queries. Here we've got a notebook where we're displaying the ability of DuckDB to fetch data directly from the GeoParquet. One of the nice things about GeoParquet, it's fully cloud native. You can index into it. You don't have to read the entire, however many hundreds of gigabytes worth of building data just to extract your local municipality's worth of building data. So that's actually pretty neat and one of the benefits to doing everything in this sort of like cloud native format. And we've done a lot of work in the past year to do better spatial indexing for all of our releases. If you tried to run a cloud query on building data on like say last January's release, it would take hours, maybe even days, to trawl through the entire thing if you were loading this remotely, because our data releases weren't really spatially indexed very well. And now they are. So these sorts of queries are much more performant. That's why the Explore site is able to download data relatively fast, and why DuckDB, with some of the new spatial extensions that they've developed, has gotten a lot faster in the last year too.
awesome.
And yeah, feel free to hit up our docs. There's a ton of different sort of command line and other types of examples of how you can get started with the data. And we're updating this all the time with new stuff.
Yeah, I guess we hyper focused on buildings today, but obviously there's other themes that are growing in transportation and addresses. So Yeah, more data, the better. And yeah, so anyway, that's it. Thank you so much. Happy to answer any questions. I want to give some special shout outs. So obviously Eric Spellman couldn't be here today, but he was an integral part. He also used to work for L3 Harris, so he was even part of a team that helped capture some of this. So he brought some great expertise there from his previous life. And then obviously Yunzi Lin was our QA lead. And was fantastic for leading a team to help annotate those control points we mentioned. I wanted to special thank to Michael Tischler and Jason Stoker. I think I saw Jason Stoker on the call. Super helpful for getting us started. Like I mentioned, when we started, we were just kind of naive geospatial software engineers. We love LiDAR. How do we start working with this? Jason was awesome being and patient with us to explain how to kind of get our hands on with the data, the limitations. And special thank you to like Esri and Microsoft, which were awesome partners throughout this. The Esri folks are really awesome too. It also has some awesome approaches they're working on. And special thank you to the LASP and Rasterio Python packages. Like one of the biggest pain points is we love Python and we love Python pipelines. And one of the first things we had to do was import LASPy into our third-party repository, which is not easy. It's basically like repackaging an entire Python binary. So, but yeah, we were so happy that somebody made this tool in Python to work with the LiDAR data. I think he's associated, Hobu or Howard Butler's associated with USGS in some way. So I just want to shout, that was an awesome, whoever greenlit the project to make that is awesome. It's really useful and enabled this whole project to happen. Otherwise, it would be really painful to do this all in C++ or kind of older languages. So, and Rasterio was really awesome for making those DSMs really easily. So I just wanted, again, and the theme of open source being awesome, thank you to the Python packages, as well as it enables to make more open source data, which is what we're giving back through Overture. So yeah, open to any questions. I need to figure out how to look at the chat window, but feel free to raise your hand or just unmute yourself.
One thing I'll address, somebody suggested a particular data set from Oak Ridge Labs, FEMA GIS buildings. And yes, this is a data set that is licensed CC by 4.0 that is absolutely perfect for ripe for the picking for Overture to pick up and ingest and use. So that's really the first thing that we look at as Overture members. Like if we get a new data set, if there are any problematic or encumbrances on the license usage for open data, then we probably would need to hash that out. But CC by 4.0 is perfectly acceptable. So.
Awesome. Thank you so much, Kurt and Ben. Does anyone have any questions for Kurt and Ben that they'd like to, voice outside of the chat? You're welcome to unmute or raise your hand.
We do have one question we haven't answered, and that's from Craig, which is about the data sources being used to derive building heights in the UK and Europe.
Yeah.
Yeah, take it away, Kurt.
Yeah, this is, I'll kind of give you the history of what I know. So basically, what was interesting is we said, oh, how well would this scale outside the US? And we saw that London and France publish LiDAR data. So our thought was, hey, we can nail this in the US. Maybe we just go process London after this, right? What was interesting was around that time, so basically, I think there's two sources of height, but it's not LiDAR at the moment. So we only LiDAR is in the US right now, but basically there's one source, which is there's a really good open building data set called Ubuco. And I don't think we conflate that, but I think a lot of that has been conflated into OSM by the community. So like just to say, there happens to be a lot of OSM heights in Europe already in OSM through the community manually conflating this. Another source is the Microsoft ML heights for now. So basically, I want to say that's probably the primary source of it in Europe. But we did think about scaling this to the LiDAR data that the UK government puts out. But I think the short answer right now is it's probably from OSM and the really active communities out there, which are conflating it from Ubuco. And I think we thought about merging that. I'm not sure if it's been done yet or not on the Overture side, but like primarily it's probably the Microsoft ML model for that. So I hope that answers the question.
Yeah, that's a good thing to call out is that we have had data sets get submitted to Overture, but when we look at them on the balance of things, if they've already been largely brought into a different source, if they're already largely included in OpenStreetMap or another data set that we're already using, then it becomes less attractive for us to try and grab that data just because the delta might be small. And this happens all the time. A lot of data is flowing into OpenStreetMap each and every day. So
yeah. And in fact, one example of this on the LiDAR side is we process New York City, but unfortunately, the latest LiDAR capture from New York City was 2013. I forgot to mention that, but a big filter for us was how recent is this LiDAR data? And like for New York City, it was 2013. So we're already pretty iffy. We wanted to only do data in the last 5 years. But then when we went and looked at OpenStreetMap, it had almost 100% coverage of heights because the community had already partnered up with New York City. So basically, New York City GIS department put out a data set of LiDAR heights, like a similar analysis to what we probably did. And then OSM manually conflated that. But anyway, it's just kind of an interesting instance where the data was older, but it was still, New York City doesn't change that much, maybe, except for some buildings, like obviously like the newer, like the Park 343 or, some of the, so anyway, it was just kind of an interesting example of it's like, that's what kind of motivated us to do. It's like, hey, if the community is active enough to take thousands of people and manually conflate all these heights, then hopefully that this will be kind of useful to the next community. So.
Awesome.
Yeah.
Thank you, guys. Real quick before we sign off, I mean, you've touched on it pretty directly, and also indirectly, the value of having such broad coverage that's accurate and validated on the national map that's easy to access. Um, I mean, the 3DEP program obviously is creating value. How do you see, like, would you be able to have produced such a high quality data set without that nationwide LiDAR coverage? And how has that contributed to your process, and the value you think that it will provide folks who are using the data you're producing?
Yeah, that's a great point. And I think I probably should have put extra large text. Thank you to the USGS producers, because
yeah,
I think if I think this would just have never have happened. I think you can, like, there's people who sell these LiDAR data points like proprietary companies, but this would have been like millions of dollars, and hard to kind of justify doing that. So I think just the fact that it's openly available and extremely accurate, like we've definitely proven that it's extremely accurate, the LiDAR data itself. So it's just, I think there's no dispute there. But I think the fact that it's it just enables use cases. Like, for example, it's kind of funny. It's almost like Overture's like, when the USGS puts that data out there, I bet y'all didn't expect that we would pick it up and do this, but it's like, sometimes we just throw the data out there and somebody's motivated or interested enough, kind of cool stuff happens. So anyway, I just want to say, like, it's kind of one of those things where I love that y'all put the data out there and then kind of encourage people to go and experiment and build. Because that's really aligned with Meta's culture too, is we love to just get in there and hack and build stuff. So I love that this was open and a nice license and had nice documentation. So super big thank you for all the producers out there who kind of put this data together. So yeah, I think that's the short answer, is this would have never happened without this kind of data being available. So, or we wouldn't have even been motivated to consider this as a problem, if there's no solution. I'll put it that way too.
yeah. Another call out I can make is that right now Overture is pretty stuffed full of big tech representation, like, medium to very large size GIS companies are in these meetings each and every week for all the different task forces. And we don't have a lot of representation from, government entities, municipalities, counties. There are a couple of them that are starting to get stuck in with us. And I'm sure there's just a vast wealth of data out there that we just straight up aren't aware exists. So, by joining the foundation or just throwing data at us, kind of like y'all have already done here in chat for us to consider, would certainly help. We wouldn't exist without all of this great open data that is already out there. And the more open data that we can get shared, the better. And I think that's part of the reason why we're trying to evangelize GERS as a thing, is that if people get sort of stuck into using GERS IDs, then that kind of has this sort of this flywheel effect of, oh, cool, I have all these GERS IDs that I can just attach to my data and I can just seamlessly integrate to Overture. And Overture is already doing the hard work of integrating all these other data sets. So that saves me tons of time. That's sort of like our eventual goal with this whole effort. So the more data and the more members we have, the better off the data set will be.
Awesome. Well, thank you so much, Kurt and Ben. So happy to have you here. It was a pleasure to learn a little bit more about your process and how you see this data being used. I mean, like you mentioned, open data, it's a cascading effect. When you just release it to folks and see what they build, and you never know what kind of solutions are going to come up through the collective power of the human mind, right? If you are interested in following along more conversations like this one, please join the 3DEP user group on LinkedIn. Also, check out the 3DEP for the Nation info hub on the NSGIC.org website. And stay tuned. I will be announcing the next interest group meeting soon. Hopefully, we'll have someone from TomTom or USGS to talk about another interesting use case or how you can use 3DEP data to solve the world's problems. Anyways, thanks a lot, guys. Appreciate you being here, and we'll see you all next time.
Hi, everyone.